Hey there, and so we're just finishing up chapter 4 this week. So you'll have 2 days that you're working on word problems with exponents and logarithms. We're going to have a class, sort of, I want to say extracurricular Zoom about answering your questions, getting a chance to talk together about credit and debit. So just come hang out on Thursday. There's not going to be a huge amount, there's not going to be material that's tested, but it's a nice chance for you to talk with each other a little bit and get some of those weird adulting questions answered. Otherwise, it's just these two problem sets on word problems. So there's going to be a couple different types of word problems that you're going to run into, both in this class and in general, that follow exponents and logarithm rules. And I'm going to talk about exponential growth and decay first, and then we're going to look at a couple of examples with logarithms. So exponential growth, if you remember, is going to just be, you'll notice that both these exponential equations are very similar. Growth just means that the r is positive. So this is the rate of growth, and then t is your time. And unlike with interest, this can be any unit. Right? With interest, it was always in years. Here, it could be whatever. Exponential growth or decay will always then also have an initial amount. So in this case, it is often P for population. So this is the initial or starting amount. And so as I said, you're mostly going to see this in a population model, but there are plenty of others. And then it will equal the population or the amount of the substance at any time starting from that initial moment. So the population in number 1 of the world was 6.1 billion in 2000. The relative rate of growth is 1.4% each year. When will the population double? So the way that you can solve this is it gives you the initial population, not obviously from the beginning of time, but from when it's starting. And so that's 6.1 times 10 to the 9th for billion, just to make it a little bit more straightforward. Then we can say that the population would then equal 12.2, since we want it to double to the 9th, still billion. And the rate is equal to 0.014 for 1.4%. So then when I plug all this into my formula, I get 12.2 times 10 to the 9th equals 6.1 times 10 to the 9th times e to the 0.014. It's positive. That's how you can see it's a growth model. T. Now the nice thing here is that these numbers are kind of challenging, but when we divide, because the population is doubling, that just means 2 is equal to e to the 0.014 t. Next thing I'm going to do is I'm going to take the log of both sides, and of course I'm going to use the natural log here. So ln of 2, the 0.04 can come down, or you can think about the fact that they are inverses, so the e cancels out. You get 0.014t. Divide by 0.014. You're definitely going to want your calculator for this. And you end up with 49.511 equals t. Now, certainly this doesn't make sense in terms of the years, the way that we measure, but what this means is that it's that many years after the initial population, so after P sub 0, which took place in 2000. So in this case, this would be 49.5 years after 2000, so 2049 would be the year in which the population will have doubled. Now with exponential decay, such as half-life, which is the model that we see here, this is, again, your basic exponential model, but it's going to be decay, which means that your rate is negative. And when it comes to half-life, your rate is actually going to be negative ln of 2 over h. So there's the negative we expect, and this is our half-life, or the amount of time it takes for a radioactive substance to decay by 50%, by half. You also might see the formula written this way specifically for half-life, where the mass is equal to the initial mass times 0.5 to the power of t over h, where again t is time, how much time has passed, over h, which is half-life. So in this case, you have 300 milligrams of polonium-210, which is a half-life of 140 days. Find its mass after 1 year. So again, we're going to use our half-life formula. Since this has a specific formula, I'm going to use this. If it was a general exponential decay, I would just use the general formula. So we have our initial mass, which is 300 milligrams. And we know that h is equal to 140 days. And t is equal to 1 year. Now, one thing you'll notice is that these two are not the same unit. So in terms of t to actually plug into the formula, I need those to match. So I'm actually going to say 365. If you want to do 365.25 to deal with leap year, you can, but that seems a little pedantic to me. Anyway, the mass after 1 year would then be 300 for the initial mass, 0.5 because it's half-life, and then t over h, which is 365 over 140. Again, you're definitely going to want your calculator for this. If you want to do it all in one line, you can. When you enter this on the calculator, it's really important that you put in your parentheses where you want them to be. So for example, if I'm doing this on one line on my calculator, I'm going to do 300 times 0.5 exponent sign, and then another set of parentheses. You have to have this last set of parentheses and close them if you want to get the right answer the first time. And so then we get m is equal to 49.237, and we started with milligrams, so that is our unit at the end of this problem. So those are your main exponential functions. There are, of course, other things that behave with exponential growth and decay, not just half-life and population. Those are just the most common ones. Logs don't generally have the same rules. One would be the pH scale. There's also the Richter scale, which is used to measure earthquakes. There's several others that are all in your textbook. I am not going to go into every single formula that you're going to run into, and I'm going to encourage you to look at those on your own. The pH scale, I'm going to show you as an example here because it's definitely the one that requires a little bit more review, since we're talking about acidic, basic, and neutral, and those vocabulary I want to review versus an earthquake. Hopefully, if you don't know what an earthquake is, please reach out, but hopefully you know what an earthquake is by the time you're in pre-calculus. So pH is, what it really is doing is measuring the concentration of hydrogen ions in a substance. So this is what H plus is the concentration or the number of hydrogen ions in a substance. And if you remember pH from science class, they go from 0 to 14, where 0, if something has a very low pH, meaning it has a very small number here, what that tells us is that it is very acidic. And 7 in the middle is neutral. Whoops. And this is famously what water is. And then 14 is called basic, or you might also have seen the word alkaline. This is why I wanted to do this as the example, so we can get that vocabulary in. Something that's basic or alkaline. And this is our pH scale. So hydrogen concentration of human blood is, well, it's supposed to be 3.16 times 10 to the negative 8 moles. Find its pH and classify it as acidic, basic, or neutral. So the first thing that you want to do is just plug that into your formula. If it's pH, you can use the formula I've given right here. If it's going to be one of the other log problems, just use the formulas from the textbook. So in this case, pH is equal to negative log 3.16 times 10 to the negative 8. And in this case, you could plug it straight into a calculator. Nice thing you'll notice here is that it's the general log, which is already base 10, and we have a base 10 number here. So there's a way we could estimate this really easily even without that, because we can say, well, this is negative log 3.16. The multiplication becomes plus log 10 to the negative 8. Log and power of 10 cancel. So this is negative log of 3.16 minus 8. Can simplify that to 8 minus log 3.16. So if you didn't have a calculator, you could say, all right, well, this is going to be a little bit less than 8, even if you weren't sure. So even if you weren't sure, you could say, oh, it's a little bit less than 8, but since 3 isn't a full power of 10, it's less than 10. We could still say that means it's going to be a little bit bigger. It's going to be bigger than 7, but less than 8. And if something is in between 7 and 8, we can say then that this is going to be slightly basic or slightly alkaline. And so that's why, if you want to type it in, you will end up with a pH of 7.500. So again, we're talking about something that is slightly basic or slightly alkaline. So when you see things like alkaline diets or things like that and people get worried about that, you don't need to unless you have a very severe blood disorder. Your blood is already taking care of it. You're already a little bit alkaline to begin with. So if you're worried about that, if you see things advertised for that, you're fine unless you have a very rare blood disorder, and in that case, your doctors have already told you what to do. Hopefully this helps. Please reach out if you have any questions about anything from exponential, logs, anything like that, and know that this is the last week of Chapter 4, which means next week you're going to have your Chapter 4 test. Look forward to